Good. Okay. Maybe we can start. It's 2:30. All right. So today we'll start a new topic. But before I do that, I just wanted to make some announcements. I said all of this on Piazza already. So the problem set 2 that I talked about last time, I posted it on Canvas. Okay. Then just to make sure nobody misses it, I posted a note on Piazza saying it's on Canvas. So go to Canvas, like problem set 1, download it. There is Lablet in there. There is a homework in there. Okay. Due a week from today. Right. So you get always 1 week for problem set. Okay. And as I said, I also handed out lab 2 today, which is early because you have the whole month to do it. It's due on April 1st. Okay. So you can use the spring break as you wish to work on labs or not work on lab. You'll still have a little over 2 weeks of non-spring break actual week time to finish your lab. Okay. So those are the 2 announcements. We will have a midterm after spring break, so there's no need to worry about it now. But just keep in mind that the exam is actually scheduled after spring break, okay, the week after spring break. All right. Okay. So with that, let's start. We want to talk about today a new topic. Essentially, this is on migration. Okay. So we'll talk about code migration, process migration, virtual machine migration. Okay. So we have 3 parts to the lecture. First part is going to be on code and process migration. Then we'll talk about VM migration and some related issues. Okay. So we will motivate why we need it. Then we'll talk a little bit about what are some issues that we need to deal. And then we'll talk about details of process and virtual machine migration. Okay. So let's talk about why we need migration. We encountered some of this already when we were talking about distributed scheduling. Okay. If you remember, when we talked about scheduling, we had a scenario where a machine needs to send some work to another machine, to a remote machine. And we said you can either move the code or you can actually move processes. Okay. And at that point, I said we'll come back to this and talk about it in more detail. And that's what we are going to do today. Okay. So if you have the ability to migrate either code or applications themselves, it gives you a lot more flexibility. Okay. And we'll talk about 2 classes of migration initially, process migration and code migration, and then we'll add VM migration to it. So code process migration essentially says you have an executing application process on one machine. Okay. You want to move it to another machine. Okay. If you have the ability to do that, you have what is called process migration. Okay. And it's also called strong mobility in the literature. Okay. So this will allow us to better use system resources. We talked about scheduling in the context of distributed applications and workstations, and we looked at Condor and other systems. Okay. The other approach is to migrate code, which means that you will actually move the code of the application and then start the application process on another machine over starting it here. Okay. So this is called code migration or weak mobility. In either of those 2 cases, the application is running somewhere else. In the first case, you move an existing process. In the second case, you just move the application code or the binary and just start the process on another machine. Okay. So there are many examples of code migration. Okay. So even something very simple like you fill a web form and you hit submit is an example of code migration, because some code with the data you process, not processed, you typed in your browser is actually going to go over a network. Okay. You can ship parts of the client to the server instead of sending the data over. So instead, a simple task of sending a query to a remote server or remote database is an example of code migration, because the code query is a simple program that the database will actually execute. So there are many examples that you are maybe familiar with, but haven't thought of it from a migration standpoint. And today we'll look at many issues that arise in this context. Okay. Yet another example is dynamic configuration. Okay. This actually now happens on modern operating systems. You plug in some new hardware. Okay. In the old days, you had to make sure that you had downloaded a driver for that hardware and you install that driver. Okay. Now, modern operating systems will actually take the hardware, and if there is no driver available, they'll go to some driver repository okay, that's out there on the internet, and look for a driver and download that driver on the fly and configure the hardware. Okay. Printers are a very good example of this. Okay. Most of the operating systems will have some built-in drivers for existing printers, but if you have a new type of printer that it does not have a driver for, it will essentially go look for a driver in a printer repository and so on. So you're downloading drivers on demand, but that concept can be made more flexible by saying any software can be downloaded on demand when you need it, rather than installing all the software you need ahead of time. So this is essentially on-demand download and use of applications. Okay. So and that's an example of code migration as well. Okay. So with that in mind, let's look at some migration models, and then we'll look at some of the issues that I think we had mentioned previously, which is how are you going to deal with processes migrating when they have to access resources. That's really where some of these problems come up. Okay. So when I mean a process, okay, an executing process, you have to keep in mind what is in the memory state of that process. That's what we really need to migrate. Okay. The memory state of the process is going to consist of a code segment, it's going to consist of the stack, it's going to consist of heap, it may have some resources allocated to it, okay, and it will have register state. Okay. So when you migrate a process, you've got to migrate all of these things. Okay. Now, we'll look at now different models to do this. I already talked about strong and weak mobility, which is, are you just migrating the code or migrating the process? So there's one dimension of migration. Okay. The second dimension is who has initiated the migration. Okay. There is always the sending machine and the receiving machine. The sending machine is where the application was executing previously, or the application binary resides. The receiving machine is where the application will execute after the migration has taken place. Okay. So you can have sender initiated migration, which is the sender has triggered it, or receiver initiated. This is very similar to when we talked about distributed scheduling. We talked about sender and receiver initiated. Same idea here. Okay. So when it's sender initiated, you actually have the sending machine do this, sending a query to a database server, or simply having a process within a distributed scheduler, not a process, rather a machine within a distributed scheduler that tries to offload a process. That's sender initiated. Okay. Receiver initiated, there are many examples. Okay. So if you think about, let's say, some downloading within your browser JavaScript from the server actually go to get a web page, the server actually sends you the web page with some JavaScript in there. That's some code that the server has sent to the browser. Okay. That's an example of code migration. You can have many other examples like this that we will also talk about. Okay. So that's the second dimension. Yes, first dimension is are you migrating a process or are you migrating code? Second dimension is the sender initiating the migration or receiver initiating it? And then there's a third dimension saying, where does the migrated entity, whether it's a process or code, execute? Okay. So your examples here are, you can execute the code in a new process. Okay. You can execute the code in the process that actually initiated the migration. That's true, let's say, in a browser context. Your web browsers have the ability to execute JavaScript inside the browser. Okay. So the downloaded code executes in an existing process, not in a new process. Okay. So you can also have something called remote cloning in context of process migration, where you create a clone of the process on the new machine. Okay. That's called remote cloning, and then you essentially execute that process on the new machine, or you just pause the process, just copy all of that state and resume execution. Okay. So many different scenarios. We will actually get into the details of some of these scenarios, but what I broadly described are different models. Okay. So we have the mobility mechanisms. You can either have strong mobility or weak mobility. That's your first dimension. Within each of these, you can have sender or receiver. So you have within each, you will see sender or receiver, and then within each of these, you will see, can you execute it in the current process, new process, and all of this kind of stuff. Okay. So this is a very high-level classification of how migration models exist today. Okay. With that background, I'm going to ask if there are any questions, but with that background, we will now get into some details of how you can make this happen and so on. Any questions on this? Okay. All right. So let's ask the hard question about migration. Okay? So at its very core, when you have to migrate a process, okay, you just have to migrate the memory state of the process, you migrate the registers of the process. On the new machine, you create a new process with that state, and you resume execution. Okay? That's the general concept of how migration works. But the hard part, why migration has been a problem for many, many years or decades even, is that your processes or applications are accessing resources on machines. Okay? Process may be accessing a file. Okay? So it may be actively performing I/O to a file. The file is on disk. You move the process to another machine. If it can't access the file, then the process will have an error when it executes. Right? That's an example of a resource. The process may be communicating on a network socket. Okay? You saw how to make sockets in your lab one. Right? You move the process. Okay? The socket is not going to move with it because the socket is tied to an IP address. Okay? Because the socket address is the IP address of the previous machine. That IP address is still tied to the previous machine. So your socket connections will break. Okay? So there are lots of problems of this sort, okay, where you cannot actually make migration work very easily because there are resources that are being accessed. Okay? And then how do you deal with these resources is always an issue. Okay? We'll see how to deal with some of the simpler ones on this slide and the next one. Okay? But then there are others that are actually harder to deal with, and we'll get to eventually VM migration later in this lecture, and we'll see how to deal with that problem. Okay, all right. So let's think about what do we do with these processes. Okay? Now, clearly, if you want the process that you're migrated to execute successfully on the new machine, it has to have access to all of the resources it was accessing previously. So somehow we have to make sure the resources that it was accessing are still accessible on the new machine. So how can we do this? Okay? There are two ways to think about it. Okay? So first is how tight is that resource bound to this process. Okay? If it's a very tight binding, which we will call that binding by identifier, which means that you want that specific resource, you cannot actually find some other resource to substitute for it. Okay? And then there is another type of binding, which is a little weaker, which says it's by value, which means that you can substitute that resource for another equivalent resource, and that's still okay. Right? So the first type by identifier was a very specific file. You're reading and writing maybe to a log file or maybe a database file on disk. If you move it to some other machine, you can't just say, here's a different database file, read or write to it. That doesn't make any sense. You have to be able to provide access to the original file. That's a tight binding. Okay? You can't replace that with some other equivalent resource. Okay? But let's say if you are trying to run Java code, okay, on a JVM. Okay? So long as there's another JVM of that same, let's say, version number, your code will run. You don't need to actually say it has to be exactly that file. You can't substitute. So here you can actually substitute that resource with another resource so long as they're equivalent in some way. Okay? So that's a little weaker binding where you could substitute the resource. So Java library, C library, Python libraries that are equivalent, so long as you have them on the other machine, you can use them. Okay? And the third one is by type, where it's a weak binding, where anything that looked like a previous resource would work. An example is a printer. Okay? So if a process needs a printer, okay, so long as there's some other printer accessible, that may be okay. You don't have to say it has to be exactly that model printer. Okay? Some other model printer will be fine so long as you can print a job or something like that. So that's an even weaker binding. Okay? So what I'm trying to say is the resources that the process accesses have different properties. In some case, they are not substitutable by any other resource. In other case, they are somewhat substitutable if you find something equivalent. In some other cases, they are very weak binding, so you can find something that looks like that resource and it'll still be okay. Okay? So depending on how tight the binding is, we can come up with different strategies that we'll talk about on the next slide. Okay? That's the first dimension. The second dimension is how expensive is it for you to actually move a resource if you have to move it from along with the application. Okay? So unattached resource essentially means that they're easy to move. So if it's a small file that your process was accessing, you can move the file with the process so that the file actually is on the other machine, can continue to read and write to. Okay? And if it's a small file, it's not going to cost a lot of resources to move it. Okay? That we'll call unattached resources. Fastened resources are resources that you can move, but the cost is high. Let's say it was a database. It's 10 gigabytes in size. Okay? Can you move it with the process? Sure, you can copy 10 gigabytes from one machine to the other. It's not a cheap operation. It's going to take some time, going to incur some overhead, but you can still move it if you want. And then the database is going to move with the application, so that application can continue to access the database file. Okay? We'll call these type of resources as fastened resources. They can be moved, but at a high cost. Okay? And the third one is essentially fixed resources. These are resources that cannot be moved with the application. Okay? Network socket is a good example, because that's tied to the IP address of that first machine. You just cannot move that socket. That concept doesn't exist. Okay? So you have now a gradation of how easy or difficult is it to move that resource. So the first one was how tightly are you bound to a resource. The second one is how easy or difficult is it. So you can move it easily, you can move it with a high cost, or you cannot move it at all. Right? So now we have these two dimensions, and we can now take these two dimensions and think about some strategies of what you can do when you're moving a process. How can you make sure the resource continues to be accessible? Okay? So here's a table that tells us what kind of strategies we can use when we design a process migration system. Okay? Here, the columns are the bindings, which is it unattached, which is easy to move? Is it fastened, which means it's expensive to move? Or it's fixed, which means you can't move it at all. Okay? And then the rows are how tight the binding is, which by identifier means it's tightly bound. You cannot substitute that resource. Okay? By value means you can substitute it by equivalent resource. By type means it's even looser binding. You can substitute it with some other class of resource, like a printer and things of that sort. Okay? Now, each of the entries in the table essentially represent one scenario of the binding, the machine binding, and essentially the resource binding. Okay? So let's take some examples, and then you'll get the basic idea. Okay? Let's take a resource that is bound by identifier and is unattached, which means it is by identifier means it is not substitutable. It's only that resource that the application wants to use, like a file that you're reading or writing. And unattached means it's easy to move. Okay? So in this case, if the process moves, what do you do with the resource? Yes. You can move the resource as well, because it's easy to move and you can't substitute it. So you have to make sure the process has access to that exact resource. So it's not like you can say, here's another file. Why don't you read or write to this other file? That doesn't work. Right? So you will see that move, MV stand move. So move is essentially the strategy you got to use. Okay? There's another thing here which says GR. GR essentially stands for a global system-wide reference. That essentially means remote access. Okay? Remote access is always an option. Okay? If the file, you don't want to move that file, you leave it there, but make sure the process can access it over a network. That's still okay, so long as you can make sure its IO goes over the network, or you mount the file on a network volume and give it access. That's okay. Okay? So you can always use that option if you want to, but the easier option is just move the file and you're done. The process can continue to access it on the new machine. Okay? Not a problem. Okay? Now let's take this other one, which says it's essentially by value, but it's an unattached resource. So in this case, you don't actually need to move it. You can copy it. Okay? You can, so that's why there's a CP. You can, of course, move it if you want to. You pay higher, pay some cost, or you can provide remote access. Okay? So you have now some more options because the binding is weak. And then you have the weakest binding, which is by type. Okay? By type essentially says that it's like a printer. So you can find some other resource to substitute it. And that essentially, you have another strategy there, which is RB, which stands for rebind. Rebind says substitute. Okay? Find some other resource that looks like it, and the process is happy with it. You don't really need to move. So you can just say, I'll just let you print to a different printer. Okay? So you have these 3 or 4 strategies, and you will see how they change for other columns. So you can move the resource, you can copy the resource, you can provide remote access to the resource, or you basically substitute the resource with some other resource that's available locally. Okay? These are the strategies. Okay? So now let's look at fastened resources. Fastened are resources that can be moved at high cost. Okay? I'm not going to go into all of those details, but let's take by identifier. Identifier means I can't substitute it. That's the resource that I have. A large database is our example of a fastened resource. Okay? Now, process moves. Okay? What do you do with the database, okay, that it's trying to access? What strategies can we use? Okay? You can move it. You'll pay a high cost. Okay? But it's better to just provide remote access. Okay? This is why you will see that GR, which is essentially says global system at reference, that's essentially remote access. That's a better strategy, because why pay the price of moving it if it's not? So you should only move it if there's going to be a lot of access to that resource. So you pay that high price of moving it, but then you have the benefit of lots of local IO. There's not a lot of IO to that resource. It's better to just provide remote access rather than pay a high cost of moving a very large database or a large file. Okay? So in this case, global reference is a better option. Okay? And that for expensive resources, by and large, we want either to remote access, which is why you will see those two, or if it's by type, you just say I substitute and I'm done. Okay, so that's that. And then we have one more column here, which is fixed. Fixed are resources that cannot be moved. Okay, so in this case, remote access is our best option. Okay, that is why you will see GR as the strategy. Typically, unless it's by type, which means that it's you can't move it, but there is some other resource available, so you can do a rebind. Okay, so you have these strategies. Now, this is not a technique, but it's just telling you what you have to do as an OS designer. Okay, so now if you're writing a process migration system, you have to think about what the processes you're migrating might do, what types of resources they might access, and you have to implement these strategies. Otherwise, your process will basically break after you move it, okay? Because you can't just run it and it tries to access the resource, it will get an error and crash. Okay? So any process migration system has to deal with these subtleties. Okay? Now, this is all fine for things like hardware resources, you can rebind them, or things like data files and so on. Okay? None of these strategies will still work for network sockets. There's no concept of moving a socket. There's no concept of providing remote access to a socket. That's not a concept that exists. Okay? So if your process is actually communicating over a network, none of these strategies will work. Okay? So in particular, in our distributed systems, you're talking about client-server applications. They communicate. Okay? You just move the server to some other machine, all the existing connections with clients will break. Right? So that problem we have not solved. Okay? And that's an important problem for us because we are talking about distributed system. But other kinds of applications that are doing IO to files, that may be accessing other types of resources, you can certainly do this. Okay? And we'll see how to solve the networking problem, okay, when we talk about VM migration. Okay? But as of now, we have not solved that problem, but other problems like files we can do. You can use these strategies. Okay, so I'm going to talk about one more thing here, which is migration in heterogeneous systems, and explain why this can also be a problem. Okay, so implicitly we assume when you're moving a process from one machine to the other, that both machines use identical hardware, okay, which means that's the same architecture, not identical hardware, but same hardware family. x86 machines, both are Intel machines, both are running the same OS. Let's say you're moving from a Linux process to another Linux process. But not all machines may be homogeneous in your system. Okay? So if you have heterogeneous systems, then this problem gets even more complicated. Okay? We already said resources complicate migration, but if heterogeneous system, you have more complicated, right? Maybe the new machine has a different architecture. Maybe it's running a different OS. Can you still make it work? Okay? The general answer is no, you cannot make it work because you can't take a binary process that's running on one machine and simply move it to another machine and expect it to work. If the first machine is Intel, second machine is x86, Intel instructions are not going to execute as is on a different machine unless you do more special things. Okay? So in general, this is not going to work at all. But people have tried to think about how can you make migration work across heterogeneous machines. Okay? One way is to actually have some layer of abstraction between the process and the underlying machine, so you can still make all of this work. Okay? And the simplest example is Java. Okay? Because the JVM is going to run on different hardware architectures. If your process is a Java process, you can still move it because it's actually executing on a JVM now, and the JVM is the one that's executing on the underlying machine. This is Java is a platform independent programming language. Okay? So what JVM does is it gives an abstract machine. The Java virtual machine is actually an abstract machine that Java processes see. So long as that abstraction is available, it does not actually matter whether underneath you are running on x86 or ARM or anything like that. You have your like a jar file should work regardless of where you compiled it and so on, right? So that is platform independent. So if you have things like JVM or intermediate code that you can recompile, you can make this one. Same with Python, right? You can have Python scripts. So if an interpreter-based language, that's still okay because you can just move Python scripts, and so long as you have that version of Python, it will still work. Not a process. Okay? I'm talking in this case code migration. Okay? Process migration is a little bit different. Okay? So when you have machine heterogeneity, things are even more complicated. Okay? Things are not going to work as well. So there are all these complications, which is why process migration, I think we've studied for 50 years, okay, never actually took off. And even in today's operating systems, you won't see anything like that unless you know exactly what you want. There are some features that might allow you to do migration, but by and large, this is still a concept that's not widely used. Okay? But we'll now see when you enter the world of virtual machines, why all of this becomes simpler for us. Okay? But if you have regular processes running just on normal machines, moving that process, hard problem. Okay? People have tried. There are systems that have tried to do that, but they make all sorts of assumptions, put all sorts of restrictions for it to work. Okay? Is this clear? Okay. So that was process and code migration. I talked about virtualization for the last two classes already. So let's now see how you can do this in the world of virtual machines. Okay? Can we move processes when they're running inside virtual machines rather than physical machines? Okay? So the answer is actually you can migrate virtual machines. It makes actually life much easier, and we'll see what techniques you can use to do this. Okay? So VMs can be migrated from one physical machine to the other. Okay? So long as your hypervisor running, you can actually move the virtual machine. It will move over to another machine and start physical machine and start executing. Okay? And more importantly, what VM virtual machine migration allows you to do is something called live migration. Okay? Live migration means that you are migrating the VM when there are processes and the OS is executing inside them. You don't have to stop anything. You can just migrate, and then the processes continue to execute. After a while, the processes magically show up on another machine and they continue execution. The application does not see any downtime or anything like that. Okay? Which is pretty good, okay? Because you don't even have to say, let's stop the application, let's move it and then start it somewhere else, which is what process migration actually did. Okay? You actually did pause and restart. But for virtual machines, you don't have to do that. You can actually make migration live. And the way you are going to do this is through what is called iterative copying of memory state. I'm going to show you some examples of how to do this. And then I'll also talk about how we solve all of the resource problems. Okay? How files are going to work when you're trying to access them, how network connections are going to work. So all of that we'll talk about. Okay? Is the problem clear? What we are trying to do? We are trying to see how to take a virtual machine. Okay? And remember, I already told you what a VM was. Inside a virtual machine is an operating system. It's our guest OS. And inside the guest, there are many processes. We want to migrate them all. We're not migrating one process now. We're migrating the entire virtual machine, which means the OS and all of its processes. Okay? Is that clear, what I just said? Okay. So I'll talk about two techniques to do this. Okay? First one is called pre-copy migration. The second one is called post-copy migration. Okay? And we'll see how they differ, but let's try to understand how pre-copy migration works. Okay? So let's take a simple example. Okay? There's a picture here. You'll see two machines, A and B. Okay? The blue box inside, the light blue box, okay? Now this one is the VM. Okay? And that VM is running. It has some OS in it. It has some processes running. We want to move that VM to machine B. So what are we going to do? Okay. What does it mean to move a virtual machine? We have to essentially take all of the memory contents of the VM and move it over, because the memory contents will contain all the OS and the processes that are executing, as well as register states and things of that sort. Okay. So our goal is to take the VM's memory, that's the blue box, and move it over. Okay. So what can we do? We'll just start copying memory. Okay. So let's say the memory is comprised of pages, as you know. Okay. So we'll take one page at a time and we'll move it over. Okay. So we'll say, let's take page 1, let's transfer it over the network. Okay. Let's take page 2, we'll transfer it, and so on. So we'll just go from 1 through n and copy all of the pages over. Okay. Once you're done with this, the new machine has now n pages from the old machine A. Okay. That's just the first copy. You just copied one at sequentially all the pages over. Okay. So what can we go wrong when you're doing this? Why is this not good enough? Contents may change. Okay. Yes. So processes are executing, right? They're not just sitting there while you're copying the pages over. They're executing. They're actively changing memory contents. That you may start a new process on this inside this VM. Okay. It will get new memory allocation, etc. So it's not like the memory is static while you're doing this. Memory contents are continuously changing. Okay. So what you have on this machine, okay, will have some pages that are outdated because those corresponding pages on the first machine have changed. It's not that every page would have changed, but some pages would have changed. Okay. So there are some pages that are still the same as machine A, but there are some pages that have now changed. So what do we do? Yes, you're saying something. Okay, so you can copy everything all over again, right? But of course, you don't have to copy all n pages, right? Because if some page has not changed, why would you copy it again? There's no need to. Okay? So what you have to do is you have to now keep track of, as we were doing the first round of copy, you keep track of every page that has changed. Okay? You're going to keep an extra bit, which is called a dirty bit. Every time a page changes, the dirty bit turns on. So you now know which subset of pages on machine A have changed since the copy operation began. Okay? So in round 2, we are going to send those pages over. Okay? We copied. So first time we copied all the pages. Second time we copied a subset of the pages. And this time we copied only pages that have changed. Is that correct? So now what? Are we done? Yes. Is it a fair operation to assume that copy operations are faster than memory updates? No, it's actually the opposite. Memory updates are much faster than copy. Yes. So the question is, when you're copying, can the entire thing be updated again? So it's not going to be that every page has changed. So you have to remember how processes work. If you remember anything from your undergrad OS class, you will remember there's something called a working set of a process. Okay. Working set of a process are the set of memory pages a process is actively working on. Okay. So generally speaking, a process may have a lot of memory allocated to it, but at any given time is going to only be modifying or accessing a small set of those pages. Okay. So not like the process goes and accesses all of its pages every second or anything like that. At any time, depending on what code you're executing within that process, you're only accessing a small part of the process. So if you make that assumption, even though memory updates are very quick, it's not like all of the contents of memory are changed. Only some contents will change. Those are precisely the working sets of all the active processes on the machine. That's what is actually changing. Okay, but that's a good question. Okay, so we did round 2. We sent only the changed pages. Are we done? You sent on first time you sent all the pages, second time you sent changed pages. Yes. Yeah, they could change again, right? It's going to take you some finite time to send pages over. Right? It's not going to be instant. Okay? The network is still going to have some overhead in sending pages. So while you send in round 2 some subset of pages, some more pages would change, right? So you repeat, right? You say, I keep dirty bit. I now will track my pages that have changed. I only send those pages. Okay. So now you may say, okay, pages may change again. So you'll keep doing this, but then you'll say, will this ever terminate? If I keep sending pages and every time some page change, I may never end up sending all my pages. Okay, so why will we actually terminate in this algorithm? Okay. Yes. So one suggestion is let's halt all processes. Then nothing is going to change. Then you change everything. You could have done that in round one, by the way. Then nothing. You would not do all of it. But you have a downtime. You are doing this live. Okay. You can absolutely do that. And there are migration schemes that will do this. They'll pause the VM, so nothing changes. You copy everything over. You have exact copy on both ends. You resume. You're done. You don't need to do any of what we are talking. We are trying to do this live while processes are executing. So process will never see a down when we still want to converge. Yes. Okay. We can have a stopping criteria which says more than 95% or 99% of the pages have not changed. Let's pause and send them out. Okay. That's a good point. But the question is, will you actually get to a scenario where you will get that many? Will there always be enough pages that have changed so you'll never hit that criteria? So that's, you're right. What you said is actually what's going to happen. But what is the reason we believe we'll hit that after some number of rounds? Yeah, you can do hard limit too. If you cannot converge, you have to take it down. Okay. So the basic concept that you have to keep in mind is there'll be some average rate at which pages are changing. Okay. That's the right rate of the process. Okay. Each time, okay, if you essentially the first time around you send all the memory content, some subset of the pages change. Let's say 10% of the page change. Okay. Next time around you send 10% of the pages. Okay. Now you have to remember that it's now going to take you much less time to send 10% of the pages than all the pages. Okay. So when only 10% of the pages have changed or are being sent, that time is much shorter than the first round. So in that round, in that time, you will have much fewer pages changing if there is some write rate. Let's say you're making 10 writes per second on average, right? So if you're now sending a smaller number of pages, the next time around, the number of pages that should have changed should be less than 10. Right? Maybe 5 pages changed. Okay? Then you send those 5, but then it takes you less time to send those 5 than it takes 10. So in this time around, if pages or processes are well behaved, of course, you may still see fewer pages. So in each round, if processes are well behaved, you should see fewer and fewer pages changing than the previous round because the round duration is short. That's the main insight. Is this clear? Now, of course, this doesn't have to be true. You might have that's a Java just doing garbage collection and it just goes and writes a whole bunch of pages. So you might find a round where the change set is actually increased. But the assumption is it's not going to happen all the time. It may happen every once in a while. You have bad luck and then the round actually becomes longer, but eventually it'll get shorter and shorter. Okay? And then we'll get to a point which was pointed out where maybe the change set is very small. Maybe only 3 pages have changed. Okay? And time to send 3 pages is quite small if you have a fast network. This is the point where you'll actually pause the VM. Okay, otherwise, you will never really convert. So we will essentially say if the change set is very small, we'll pause the VM. We'll now send the remaining pages. At this point, they were identical copies. So nothing is different. So nothing will change at this point. So then you can simply say if the 2 VMs are identical, I'm just going to resume the VM on the second machine. And then I'm just throw out the first VM. So this VM will be identical here. We'll just start executing it here. And we throw that one out. Okay? And then everything has moved. All your processes moved. The OS moved. Okay? Because you're just sending the entire VM's memory over. You're sending all the register state over. So it's an identical virtual machine copy. Right? So you just resume execution and everything just continues as is. Okay? Yes, your question and your question.
Yes, what if the third round on the process change the page that is being sent on the first round, which is being marked as unchanged?
Yeah. Question is what happens in the second round? You actually you modify a page that was marked as unchanged in the first round. That's your question, right? So it doesn't matter which page changed. Okay? We are not saying that in each round, the pages that are changed are only the ones that were a subset of the ones you sent. Okay? Any page can change at any time. Okay? The point is the number of pages has to keep shrinking, not which pages are changed. Okay? So first time you send 100, then maybe it takes you 1 minute to send those pages, and then 10 of them change. Then next time you send 10. So to send 10, you should take 1/10 of that time. So you should take 6 seconds to send those pages, not 60 seconds. And in those time, you will see even fewer changes. Which page change doesn't matter from our perspective. It could be something that was sent in the first round. You just keep tracking your dirty bit. Every time you say, these are the pages that changed since the previous operation began. And that's all you send. That's not a problem. Okay? You had a question there? Yeah.
How do we qualify with that now?
Okay, so question is, how do we qualify the downtime versus not? So the point is that downtime, you will not perceive, you as a user will not perceive a downtime if it is so small that it actually, that from an application standpoint, you can't actually see anything, right? So let's say it's 1 millisecond. What is going to happen? Maybe you send a web request, the web response takes 1 millisecond longer or something like that. So from a user's perspective, it's almost not visible change. Okay? But there is a very tiny pause. A pause could be a few milliseconds or something like that, not minutes or hours or anything like that. That is noticeable, right? But your pause is so small that you actually cannot perceive it. Then from your perspective as a user, there is no downtime. Okay? So the downtime is from what a user is perceiving. Okay? So if the user doesn't know or care, it's okay. Because you might have other reasons, the machine suddenly slows down. You may also see some worse performance. So it's very slight and it's not observable. Not observable, I shouldn't say not observable, not perceptible. Right? So you cannot perceive that as a down. So that's what will qualify as live. Okay. Is there some more question? Yes. So you are saying the number of writes is less than what? The number of writes is less than the number of copies. So first of all, we are not talking about file writes. We are copying page writes. Okay. Yes, the number of page writes does not have. So you can have as many page writes as you want, but within page writes also there is a locality of reference. Okay. Because the working set of your process is small, you can have millions of page writes. They are just writing to one page. Only one page has changed. It doesn't matter how many writes go to that page. Okay? So it's not the number of writes as much as the number of pages that are being modified. So you can write many times to a page, still at the end you have one page that is, right? So that's our observation. Okay? And that is because working set, this is how processes work. Their working set is typically small, even though their memory contents. That is why we actually get this. If you have random writes, this would never work. Because randomly you keep writing to some random locations, you would actually not converge very well. Okay? But because you have this behavior, it works. Yes, question. Question is there synchronization and how do you deal with it? So no synchronization, right? So all you are going to do is you are going to say, I am going to start a copy, okay, initial copy, okay, and now from now on, whenever the OS or a process write to a page, you actually have a bit that you flip for that page in the page table, perhaps. Let's say the page has changed. That's all you need. So you are just keeping track of which pages. Once I start this write, from my start of the write to the end of the cycle, you just have to keep a list of pages that have changed. That's all I need. Doesn't matter where you write, how often you write. You just have to give me a list. So next time around, I work with that list. I start round 2 and say, now I have to transfer n instead of n. I have to transfer k pages. I say, keep another, you say, let's start another list. Okay, keep track of dirty bits, and that's all you need. So there's no locks, none of that is required. You're just tracking which page contents are being written to, and you only care about pages. You may write 100 times within the page, till it's one page right from our perspective. Okay, your term question is. Okay, so how is network state handled? I have not come to that. Yes, we are going to come to. We haven't finished. Okay, we are there's still some steps remaining here. But is this clear? What is going on? Okay, so here are all the steps, right? So you enable dirty page tracking. That means now you got to track every time a page is written. You basically flip a bit. So I have a list effectively saying which pages are being written to. Okay, so now you say I will start one round. I copy all the pages to the destination. Okay, and then you have another round which say copy all the pages that were dirtied in my previous round in this round. Okay, and then you repeat the third steps over and over again. So this is why it's called iterative copy, and hopefully our dirty pages are going to keep shrinking. Okay, that's our assumption. Sometimes they may grow, but eventually, hopefully, they'll converge and you will shrink. Okay? So you'll do this until the rest of the memory pages is small. So if you end up in a round where the number of dirty pages is very small, you say, okay, now is a good time to actually pause the VM. You stop it. Okay? So you'll actually stop executing. The memory contents are still the same, but it's not executed. No processes are being scheduled. So the pages are just sitting there as is. No changes are being made. Then you copy the rest of the VM pages. Okay? Then you copy all the other state, which is like registers and so on, also to be copied. But that's a small amount. So you can copy all these remaining pages and the registers fairly quickly. And now you have an identical copy on both machines. You resume execution. Okay? But you also have to do some extra work. So there's a last step here, which is you send what is called an ARP packet to the switch. Okay? So the Ethernet switch. So we'll assume these two machines are connected over a network, but there's an Ethernet switch here, which is not actually shown. Okay? So you have to tell the switch that the VM has actually moved. Okay? Now the important thing here is because this is a virtual machine that you are moving, the virtual machine has its own IP address, which is different from the physical machine's IP address. Okay? Because a virtual machine will have its own logical Ethernet card. Remember I said last time, or maybe 2 classes ago, the virtual machine has its own interface, okay, which is just mapped to the physical interface, but it's a distinct interface. So the VM has its own IP address. Okay? The physical machine has its own IP address. The physical machine's IP address cannot move, because that's bound to it. But the VM's IP address is tied to the VM. It has nothing to do with the physical machine. So if you move the VM, its IP address can move with it. Okay? If the IP address can move, then the connections don't have to break, because you are still communicating with the machine with a specific IP address. That machine is itself moved. Because all you need to tell is the Ethernet switch saying, for this IP address, send packets this way rather than that. So that's what the ARP packet does. ARP essentially tells the switch saying there's a machine with the IP address connected to this port as opposed to that port. So all subsequent packets start flowing to machine B and land at the VM. Okay? So because the IP address is no longer now tied to a physical machine, it's tied to a virtual machine, we move it, okay? And all your connections just stay as is. So nothing has to change, because all the client packets, just the network takes care of delivering them to now machine B, which is where the VM resides. Okay? So you don't really have to do anything in this case, okay? Because the IP address is movable. So we solved a big problem in this case, which is all the networking issues are resolved. Okay? The file issues not resolved yet. Okay? Because we just moved the memory contents. Right? There are also files that the processes may be accessing on this disk. Okay? We did not move them. Okay? So there are 2 ways you can handle this. Okay? You can either say all the files reside on a network disk, not on a local disk. They reside on a server. Okay? The files are on a server. I don't need to move them. I can access that server from machine B. Right? So I just keep all my files on the file server. You never keep any important files on local disk. Then I don't need to move anything, because that server is accessible from either machine. That's option 1. Okay? Option 2 is I actually do a disk copy of whatever directories I want as well. Okay? And this will have the same problem as memory copy. I'll copy some files, but you are reading and writing to those files. The files may change. So I do multiple iterative copy of disk contents, and hopefully, just as the memory contents, eventually you could pause. You can also do this for disk. That's going to add another layer of overhead, which I didn't show you. Okay? By and large, virtual machine migration will assume that you keep files on a network drive, so you don't need to move files at all, because copying files is actually slow. Disk is much slower than memory. Okay? So you don't want to do that if you can avoid it. But if you have to, you can use the same iterative process. Okay? Is this clear? All right. So that's pre-copy. Okay? Now everything is moving live. We didn't see any downtime. You didn't have to really worry about it and so on. There's another way to do exactly this process, live migration, which is called post-copy migration. Okay? Much fewer steps here, but you will see that essentially it does the same thing, but there are some pros and cons. Okay? So in this case, what we are going to do in post-copy is, if you want to do the same thing, you have machine A and machine B, you want to move the VM. Okay? First step is you're going to pause the VM. Okay? And you better pause for a short amount of time, otherwise this is not live. Okay? But we'll start, the first step is you'll pause the VM, and you'll just copy the register values over, which is a small amount of state. Registers, 20 registers, 100 registers, 100 bytes or something like that. So you'll just copy it over. Okay? So now on the machine B, you have a blank VM where all the state is still on the first machine, but all you did is you copied the register over. Okay? And some small amount of state like that. Okay? And you will resume execution. Okay? So essentially, the CPU will essentially try to execute an instruction. Okay? And it'll try to access some memory content. And memory content doesn't exist because you never copied anything. It still resides here. And remember, this VM is paused, so nothing is changing there. Okay? So you will get something like a page fault. This is basically like virtual memory. You try to access a page that does not exist in RAM. Okay? So that page actually exists on the first machine. So because all you have is registers and a blank VM, first time you access memory, you'll get an equivalent of a page fault. Okay? Then you basically, what do you do when you get a page fault? You try to service it. But instead of bringing the page from disk, you'll go to that memory content and you'll bring that page. Okay? You got a page. So at this point, one page has been copied of maybe tens of thousands of pages. Okay? You will continue. Okay? Maybe the next time around, you access another page, okay, which also doesn't exist. You'll get another page fault. So you will essentially bring some pages over. If you bring enough for the working set, okay, then you will not get page faults for some time. At least you'll execute for a few, maybe some tens of thousands of instructions or something like that. Then you may get another page fault. The working set changes slowly, and you bring more pages over and so on. Okay? So you will essentially fetch memory on demand. Okay? So in this case also, you pause for a short amount of time. You copied the registers and you resumed execution. And then you have blank. You start with a blank memory. And each time your code or the instruction is touching something in memory, you will essentially treat it like a page fault because that memory content doesn't exist and fetch things on demand. Okay? But you don't want to keep this going for a long time. Otherwise, it might take you hours or days for all the memory contents to be transferred, because you want to make, then you will need a page fault on every single page before you bring it over. Okay? So while this page fault is being serviced to get the pages over, you will also start a background copy. Okay? You will slowly start sending pages over one at a time. Okay? Any page that hasn't been faulted in, you will just go and start sending them. Okay? So there are pages are arriving in the background. In the foreground, as you're executing and you touch a page that is not yet fetched, you bring it through the page fault. Or otherwise, eventually it will come through a copy. Okay? And you have to copy pages exactly once. Okay? But either you page fault, you bring it in, and then you modify it on this machine, or it comes on a background process and it arrives eventually. Okay? So the amount of memory copying you're going to do here will be much less than the previous case. In the previous case, many pages may have to be sent repeatedly if they're changing frequently. Okay? So the amount of memory transfer will be higher. Okay? Here, each page only goes across the network once. Okay? So much less memory overhead. Okay? but it's a trade-off, okay? Because you're reducing memory overhead, but you're incurring a performance overhead, because the first time you start executing, there will be a lot of page faults, okay? So the process will stall. Page faults slow down the process execution, okay? So until you get enough pages, you will get a lot of page faults. Application execution will slow down, but once enough pages come, you will start executing at normal speed. Okay? So you are trading memory overhead for some performance overhead. Okay? So either approach will work. It'll still give you live migration, but in one case, you will essentially pay more memory cost to reduce the impact on application performance. No less downtime, no impact on performance once it resumes execution. In the other case, you reduced memory overhead, but you have some initial performance hit when you resume execution on the other machine. Okay? And the reason it's called post copy is copying is happening after you start executing the VM. In pre-copy, copy happens first, then you execute the VM. That is why it's called pre or post copy. It refers to with respect to when the migration has happened and the VM has executed, started executing. Is this clear? Okay, so two techniques. By and large, most VMs actually use pre-copy. You'll use any of the VMs that we've talked about so far, not VMs, rather hypervisors. They all use pre-copy migration because that's more standard, but some actually have implemented post-copy as well. Okay, so let me show you that whatever I said in pictures here. So there are two pictures. This x-axis is migration time, okay, in terms of what is happening. Okay, the top one is showing you all the steps being performed in time, how long they take in pre-copy. The lower one is actually showing you post-copy. Okay, so green is when you start, okay, and then you'll see pre-copy round 1, round 2, so go round n, then you pause, okay, copy remaining dirty pages. So that red one says this is when you pause the VM, copy the remaining dirty pages. You do that R packet to tell the switch that the VM IP address moved, and then you restart. Okay, so that's the amount of time it's going to take you. Okay, this is what happens in post copy. You pause, you move the VM state, which is just registers, you restart. Okay, that's all your pause was. And then you have post copy where you are pre-paging, okay, either using a background process or demand paging using page faults, and this may take some time. Okay, and the process is executing while this is happening. Yes, it's either happening in the background or in the foreground as you take page faults. Okay, so in terms of how much time each of this is going to take, it will depend on how quickly you want to run that background process, obviously. Okay, the background process aggressively sends data over the network. If you're running maybe a web server or something like that, okay, on that machine, and the web server may slow down because it's seeing interference, lots of memory pages arriving. The web request will actually start seeing interference from other requests. So you might not want to be too aggressive in terms of how that background process copies state over, especially if you're running network servers on your application. Okay? Otherwise, you can send it fast. It's okay. So that will dictate how long this process will go on. Okay? And that process is in rounds. And as somebody said, if you don't converge after a while because you have some badly behaved process that keep changing lots of memory, only way is you actually have to take a downtime. You will pause and just send the remaining pages. So you won't keep trying for many rounds. You'll have an upper bound, and hopefully you'll converge before that. Otherwise, you say this is what I can do. So I'll just pause and just send the remaining. So there is a bound there in terms of rounds, but the bound may be high in terms of how many rounds you will incur first. Okay, yes, question. Is there any hybrid approach? Yeah, you have a new approach. That isn't one that has been proposed, but what you are saying is something saying start some pre-copy and then do the remaining as post-copy. You could do that. You could say, why not just track the working set, right? Pre-copy the working set so that when the application start, they don't see page faults because you moved the pages that are most important to them and then page in the rest or bring them in the background. Could come up with technique. I don't think anybody has done that, but that's something you could certainly try. There's another approach that's a hybrid. Okay. All right. So that is VM migration. And the last thing we are going to look at in the next 15 minutes or so are container migration. Okay? So in container migration, we'll look at all possibilities. We'll say, okay, it's fine to take downtime, show how to migrate the container. And if you want to do it live, you will have to do something like whatever we did in VM migration. Okay? So we'll see various techniques. We'll see something called snapshot. We'll see another technique called checkpoint resume, also called CRIU, as we'll see in the Linux world. Okay? So by and large, now we'll talk about 3 different types of migration. Okay? And we'll talk about cold migration, warm migration, and hot or live migration. Live migration we already looked at in the VM context. Now we have containers. Remember, containers are simple sandbox applications running on a machine. So if you want to move a container, you don't actually have to move the OS. You only have to move that process and its state. So it's much closer to process migration in that regard. Container could be a single process or a small collection of processes. That's all we are migrating. In VM migration, it's everything. Okay? OS, all the processes, you can't just say migrate only one process. You got to migrate the whole VM. In container migration, you can migrate only a container, which could be as little as a single process or some collection. Okay? So 3 different techniques. Cold migration essentially says, I am going to migrate a container, could also be a VM incidentally, that's already been shut down or paused. Okay? So what happens in cold migration is when you pause and the VM, all of its memory state actually is returned to disk. Okay, that's what happens. Then you can resume. If you remember, when I showed you the demo, I had a paused VM, I pressed resume, and it basically read the memory state and it started executing. So when you actually pause a VM in a hypervisor, it will take all the memory state, it will pause the VM and just copy all the memory state to disk. Okay? So the disk contains a replica of whatever was in the memory. Okay? So as you can imagine, cold migration is very straightforward. It's already a paused VM and the state is a file. Okay? The memory state is essentially a large file on disk. That's a copy of all the pages that were in memory that have been written. Okay? So in this case, all you need to do is copy that memory file over. Okay? And you might actually have to copy the virtual disk file, which is the disk itself, if it's not on a network. Okay? And then you load it up and you're done. Okay? There's no question of live or anything like that because already a stopped VM. Okay? So you're essentially just copying a file and restarting the VM. Okay? And you can actually do that if you have any of these. I don't know if any of you have finished the lablet already, but if you have your virtual disk file, okay, if you actually go and see the files you created when you created the VM, okay, and you pause the VM, you can literally copy that entire directory over to another machine, so long as you have your either parallels or virtual box or whatever it is that you're using, you can just resume that VM elsewhere. Okay? It'll just look like you just started it there. That is essentially you did a manual cold migration. You just copied the entire state of the VM and you started, but you can also automate it. Okay? So that's cold migration. Warm migration says, so in cold migration, you don't actually have to copy the memory state. You can just copy the disk state and reboot the VM. So you lose the process information, but you reboot the VM. In warm migration, you copy the disk state and the memory state. So you actually have a suspended set of processes that you just resume as is. Okay? So that's the difference between cold and warm. In both cases, the VM migrates and there is a downtime. In one case, you resume processes. In another case, it's cold start. You just say, I'm just going to reboot it from scratch. It's like I just rebooted my machine and lost everything that was running. But the VM will start executing, and then you can restart processes if you want. Okay? So this does preserve state, but it incurs downtime. Cold migration does not preserve state. Live migration, because there's no downtime, so everything is preserved as is. Okay? There are 3 techniques, okay, and we'll see how to do them in container. Is this clear though, what we are talking about? Okay. All right. So our basic approach to doing any of the first 2, okay, the live migration we already saw how to do. Similar idea will apply to container. But for the first 2, we'll use a technique called snapshots. Okay? A snapshot, what is a snapshot? Snapshot is actually a general concept in distributed systems and operating systems, okay, but we'll use it here in a specific way. Snapshots essentially mean a point in time copy. Okay? When you take a snapshot of, let's say, a disk or a VM, you're taking a copy of that VM as it existed at that instant. Okay? The copy may change after the snapshot. That's okay. But we are saying at time t, tell me what the VM memory content look like, or tell me what the disk content look like. Okay? That's your snapshot. Okay? It's widely used in many different contexts. So one example where snapshots are used are disk backups. Okay? So you might think of so there are many systems where you will run a nightly backup process just so that if the machine dies or something, you have a backup somewhere. Okay? But you think about how a backup process works. Okay? It is going to take copy of all of the files on your machine and transfer it to another machine. Okay? But since you're doing this while the machine is actually executing other processes, the same problem will occur that we had in VM migration, which is files are actively changing on disk. They may be written to while you're copying. Okay? So if you take some files from 10 minutes ago and some other files from now and some other file later, what you may end up is some inconsistent state of your disk where you have some newer file, some older file. You don't know what this backup actually means. Okay? So one way to take a backup is to say, let's just take a snapshot at midnight. That's the disk state that existed at midnight. And I'm only going to copy that snapshot. If things have changed after that, let them change. That's not going to be in my backup. So then my backup is, I have a midnight backup. So that is exactly what the disk looked like at midnight. It may have changed since then. My backup didn't capture that. But I have at least a consistent version of what is there. I'm not copying files as they're changing and copy something inconsistent. Okay? That's one example. And you can do similar snapshots for many other reasons, not just backup. But in our case, since we want to migrate the process, one way to do this is to say, let me take a snapshot of the memory. Okay? And I'm just going to that is basically a point-in-time copy. I'm just making a copy as it existed at time t. I'm just going to migrate that copy as is on another machine. And if I resume execution, I'm resuming execution from the time the snapshot was taken, not from the time how the VM actually is now. Okay, so I'm resuming execution from the snapshot time t, not current time t prime. Okay, so long as you're willing to do that, that's still okay. So you can take VM snapshots as backups. So you can resume from a snapshot. You can do the disk snapshot. Many file systems actually allow you to do disk snapshot. So you can, even on a Mac, you can actually take a snapshot of your disk. Okay, so if your disk, some files get corrupt, you can actually roll back to your previous snapshot. That's what Time Machine does, incidentally. Okay? You use Time Machine on a Mac, is actually taking snapshots, so you can roll back to a previous state. That previous state is essentially a snapshot of what your disk looked like at some previous time. Okay? That way you can undo any bad things that happened since that snapshot. Okay? So in this case, the same thing. You take a VM snapshot, you copy it over, okay? And then you resume execution. So you will have either a downtime or your actual data may have changed. So what you're restoring is a previous time. Okay, you resume from a previous time. Yeah, so that's one way you will do a snapshot. Now you might say, isn't this expensive? To take make an actual copy of a disk or memory, is that an expensive operation? Or how do you do it consistently? Right? Because let's say it's live, VM is executing, in memory is changing. I want to take a snapshot at time t. Okay? Unless I pause the VM, how do I make a copy? Because if it continues to execute, the page gets overwritten. I don't have the page. If I haven't copied it by then, it's already gone. Right? So the way you're going to do this is using what is called a copy on write mechanism. Okay? When you take a virtual snapshot, you turn on what is called copy on write. Okay? So what this will do is, from this point on until you're finished copying all of the memory content, if you change a page, okay, you will not modify the original page. You will actually make a copy of that page. So the original page still exists, and there's a copy somewhere else. Okay, this is why it's called copy on write. It's also called COW, C-O-W, which is copy on write. Okay? So this allows you to preserve the state as it existed, and as modifications are being made, you make a copy and you start modifying that copy. So the original contents are still there, so you can copy it out or do whatever you do. Okay? So this is called a virtual snapshot. It makes taking snapshot very lightweight. Okay? You don't actually have to copy anything. You just take a snapshot, and then you can just go and look at what existed. This is how your Mac or any other backups actually work. They don't make a real snapshot and then start backing it up. You just make a copy, okay, and then it has a preserved copy. And if you modify a file, it will actually make a copy of that file. So there's an old file and a new file. This is why when you have your snapshots on your disk size will increase because there are old copies of files hanging around on your disk. Even though you may have deleted files, okay, if they exist in a snapshot, they will still be there on your disk. Only if you roll back to previous state, you will see a deleted file. But they won't actually reclaim space unless you delete the snapshot itself. Okay? Same is true here. Okay? They're useful for rollback, which means I want to move back to a previous state. They're useful for migration and all kinds of stuff. Okay? So it's a useful technique to use. If you're doing a lablet, you can actually go into your hypervisor and see how easy it is to take snapshot. You can just say make a snapshot and it'll create a copy for it. And you can resume execution from a snapshot, or you can resume execution from the current state, and you will see the difference. Is that clear? Okay. So let's now talk, assuming we have notions of snapshots and so on, how to do war migration. Okay? War migration is usually done using what is called checkpoint and restore. Okay? So in this case, there is going to be a downtime. Okay? So it's much simpler than doing live migration. Okay? So what war migration will do is, if you want to migrate a VM or a container, in this case, from one machine to the other, you'll first pause execution of that container. Okay? So memory state will not change. Okay? Since it's an OS, other things might change, but this container and its memory state is not changing. Other things are still running. Okay? And then you are essentially going to do a checkpoint. Checkpoint means you take the memory state and you write it to this. That's called a checkpoint. Checkpoint is similar to a snapshot. It's a copy of that container, in this case, as it existed at this time and you paused it. Okay? So you checkpointed the state, which means you save the memory states of the container to disk. You copy that checkpoint. Now that's a file that you created. Okay? You copy that file to another machine. Okay? So now the memory contents of your container have appeared on another machine, and then you instantiate a container and start it. Okay? So you will essentially take a paused container and you'll resume execution. Okay? So essentially that's what is going to happen. So this is a simple way to do process migration by pausing, writing the memory contents of the process. In this case, it's a container, okay, that contains it, copying it over and resuming. Okay? But everything that we have talked about earlier in the lecture still holds. Okay? If that process was actively, it's a Unix process, it could be Python script, it was accessing files, just moving it to another machine didn't solve anything. Okay? You better give access to that file. Okay? And containers are not VMs. Your container had an active socket connection. You did this, socket connection will break because containers don't get their own IP address. VMs get their own IP address because that's a full emulation of a machine. Okay? A container is simply a sandbox for an application. The application doesn't get its own IP address. IP addresses are bound to machine. So when you do this, you got to keep in mind that some things will not work as is, especially if your process had active socket connection or it was accessing files. You got to make sure all of those things are handled manually. Either you got to restart the process so that it gets bound to a new socket, okay, and things of that sort. Okay? So this is actually implemented in Linux. It's called CRIU, which is checkpoint and restore in user space. You can actually use this to suspend a process, suspend a container, write it to disk, resume a process. So it's a set of command line tools that allow you to pause, and then copying is manual, and then you restore. Okay? And this is how Linux is going to copy containers for us. It's not live in this case. Okay? It's essentially because you do checkpoint, suspend, checkpoint, restore. So there's going to be a downtime. Okay? But you will basically incur downtime. If there are sockets and so on, you can't really move it unless you have sockets tied to, not sockets, sockets are tied to logical addresses that you create and you move a logical IP. Okay? So how the Linux world addresses it is you create a special IP, logical IP address on the machine. You tie the logical IP to the physical IP. Okay? And then when the container moves, you move the logical IP because you can't move the actual IP address and move that to another machine. So even though you can't actually have an IP for a container, you create a logical IP that's dedicated for the container. Okay? So those are tricks you can play in order to deal with the same type of issues. Okay? So that's how you can actually do all of this in Linux. Okay. So one last thing, and then I'm going to end, which is you can think about viruses, malware as also being migratable code, because that is essentially what happens when you have some malware. You click on some link, it downloads some bad code, the code migrated from some other machine, the machine actually gets infected and bad things happen, right? So that's essentially a receiver initiated migration, because you just got a phishing attack and your machine got compromised. So that's an example of code migration in an unpleasant way. Okay. There's also sender initiated, where the virus is actively attacking your machine, finds some bug in the machine, and then takes over your machine. Okay. That sender initiated, where viruses are actively spreading. Okay. They're actively looking for unpatched vulnerabilities on your machine. They exploit that vulnerability, and then they are the ones that are actually downloading code, even though you didn't do anything bad. The machine just had a security flaw. Somebody exploited it and then downloaded it. So these are also examples of mobile code. Okay? Not something that we want to actually have, but they do exist, and they're using similar techniques to what we talked about here to essentially propagate bad code in this case. Okay, so we are going to end it here and continue with another topic next time.